and share. So we are going to start with the Holtz method. Okay. The Holtz method is a forecasting procedure that works on time series with linear trend. The general equation will be y of t is b0 plus b1 of t, because that's a linear relationship between time and the time series. And our objective in this analysis is to identify the b0 and b1. If you use the regression, it's directly these two. If you use the Holtz, it will be a companion of these two. Just touching for briefly the regression, here we have a time series that try to make a prediction of the number of demand for beds in a hospital. So the hospital is looking for some subsidies from the government because they want to expand. So they want to show that the demand is constantly increasing. That's where the need to forecast comes from. In order to obtain the prediction equation based on the regression, we'll run the regression. As you know, usually with data analysis, and we'll get an equation, and then we can even test to see that a linear trend exists. So in data analysis, the y is the time series. As you see, there are 40 months of monthly demand collected. And then x is the time itself. So to obtain the equation, here you go. So the equation is here, 262 for beta 0, 3.47 for beta 1. It tells you that on the average, the increase in demand for beds per month is 3.47. That's based on the model, but the only thing is to test to see if this is a reliable number. So you test equals to 0. If it is 0, then there is no need for trend. And if it is not 0, then you have a slope and linear trend does exist. The test is done with the p-value. And in this case, the p-value is so small that you reject easily the null hypothesis. So beta 1 is not 0, and there is a slope, and therefore trend exists, and this number can be used. This is if you're asked to show that trend exists. In several questions that I asked you is always show that it's justified to use the linear trend model. Okay. To perform a forecast for this time series, then we'll make a forecast for period 41. That's the first month into the future. So it will be 262 plus 347 thus times 41. So you have a forecast for period 41. Then I want to go to the Holtz method. Actually, before, if I go to the next tab here, I placed here the linear trend based on regression part of the template that I gave you for linear models. It has Holtz and it has linear regression. Holtz will appear next here and here. So this is the multiple regression. Not the multiple regression, the linear regression. Okay. So to work with the template, you'll have to enter the data first here, then the number of periods in the data. And in case you want to make a forecast, you say for how many periods. In this case, I selected 6 periods ahead. If you want to make a prediction interval, produce this, and you want to use it for making decisions in the future, then you enter the confidence level here. Okay. So before I go to the Holtz, I want you to pay attention to just one observation. Suppose the question would be, say, can you argue that in 6 months from now, the demand for beds per month will exceed the current demand? Well, the current demand is 374. So current means now, month 40. And the prediction interval with 90% confidence is between 394 and 449. Well, 394 is more than 374. So the whole interval, because this is the upper bound, that's the lower bound. If the lower bound is more than 374, the whole interval is above 374. And with 90% confidence, you can tell that in 6 months from now, based on the regression, demand will exceed the current demand. In fact, even 1 month from now, it will already exceed. So just an application of the prediction interval. So that's for the linear regression. Now I'm going to the Holtz. Same problem, okay. Let me hide this, I don't need it right now. Okay. So the Holtz method, as opposed to the linear regression model, is one in which you use the information from now and backward in a way that reduce the weight or reduce the relative importance of the information as it becomes older. So if, and it allows you to make updates to both beta 0 and beta 1 every time you move to the next time period and new data becomes available. So because of that, the Holtz, if you look at the red, these are the 1 period ahead forecasts. Look what happened here. It is changing its slope and tracing the time period better, the time series better than the regression. The regression, for example, would be one straight line. That's how it looks. You see the regression? Regression does not allow to change slopes. So if you notice, the regression has a drawback because at the beginning, it was predicting above the time series, and then it was predicting under, and then it was predicting again above. And if you continue the line to extrapolate to make a prediction, it goes above the line here, and the time series is moving in a different direction. So when there are changes like this, the regression is not going to perform well. And indeed, we'll look at the MSE later, and you'll see the difference between the holds and the linear regression. So in the Holtz method, you start at the beginning like an exponential smoothing. You start at the beginning because you build the forecasts gradually, one at a time. So if I need a forecast for period 41, I cannot perform this forecast if I didn't know the forecast for period 40. I cannot perform this forecast if I didn't know the forecast for period 39, you see? So that's why you have to start at the beginning and move forward and build it one at a time. The procedure works like this. You go to period number 2, and you start with L. L is for level. That's the level of period number 2 is the point where you are going to make your next forecast. The level that you make your forecast from. So L2 is Y2 because this is what you have at period number 2. You need to start somehow related to the information that you have collected. Why don't you use Y1? Because you are in period number 2 already. But you use Y1 for the trend. The trend is just the local slope. Now, in period number 2, if you are at level that is, say, 100, and in period number 1, you were at a level of 80, so the trend between 1 and 2 equals to 20. Therefore, the trend of period 2 will be Y2 minus Y1. If you look at the numbers here, so L2 equal to Y2. Y2 is 248. And then T2 equals to Y2 minus Y1. So T2, Y2, yeah, is 248 minus 241. 248 minus 241 equal to 7. That's how you put it in the template. The template is putting it on its own. You put the data here. Okay. Now we move to, and now we make a forecast. Since you know where to start in period 2 and how to move to period 3, then you add them and you get a forecast. So now you can move to period number 3. Now you first start with a level. It's the level of period 3. Now comes the Holtz based on exponential smoothing. Okay, so look, in period 3, I know what is the real Y. That's the recent data. But I also have an estimate of the recent data that was done before based on the previous data points. 255 is based on Y1 and Y2. So one piece of information is the recent, another one here is based on the previous ones. What do? You weigh these two, like exponential smoothing does. Alpha times the Y3, and 1 minus alpha times the F3. F3 is 255. So here, I'm using alpha equal to 0.55. The gamma will be explained in a minute. So L3 equals to alpha times the new Y, 1 minus alpha times the old forecast for period 3. Give you 248.4. Okay. The reason we see different values, let me put here so you'll see the same values. 0.55 and 0.15. Yeah, now you can see that. 248.4, 248.4. Now come the issue of the trend. Okay, so the trend is applying the same concept. You have a gamma, which is a value like alpha. Both are called smoothing coefficients. Both are between 0 and 1. And the reason we are using a different letter is to allow for a different value for smoothing the trend than when we smooth the level. Okay, so we have here L3. Wait. You have here T3. You have gamma that will multiply the new estimate of the trend. It's new, I'll tell you why. And then you have 1 minus gamma times the old estimate of the trend. Why is this the new one? Suppose we just found out that our level of period 3 is 200, L3. This means that at period 3, I'm going to start a new forecast at level of 200. And the previous level in the previous time was 150. So the two beginning points have increased by 50 units in one period. That's an estimate of the trend. And therefore, the new estimate is L3 minus L2. So what do you have? Gamma times L3 minus L2, 1 minus gamma T times T2. Here it is. 0.15 times L3 is 248.4 minus 248, which is L2 taken from here. 1 minus 0.15 times the previous estimate of the trend, which was 7. You put it here, and you get a new estimate. Once you have the new estimate of the trend, you can create a forecast for period 4. You take the level and you add the trend. This is the trend method. Sorry, this is the Holtz method. You keep working down the line here all the way to period 40. You keep doing this for each period and create a new forecast, new forecast, new forecast. And all the time, note that the new forecast is using the most recent information, that's the Y, and the previous forecast that includes all the information behind. So we do this until we hit period 40. At this point, we can create a forecast for period 41. L40, so I'm just, since I'm not going to do it 40 times, neither do you. If you have a template and you have results, you can use them. Like I do now, L40, I copied it from the template. 378, and T40, 1.1. Okay, these two. So now I can create a forecast for period 40 plus 1. I say 40 plus 1 because I do it in period 40. 378 plus 1.1, you get 381.02. There is a small discrepancy because I rounded numbers. But you know what? 379.49, okay. That's for period 41. Now, I want to make a forecast for period 40 plus 2. I can't use the procedure from before because I don't have L of 41. I don't have T of 41. I don't have them. For this, I have to have the Y here, but that's the whole point. The Y is not known. So you use the best information that you have, which are these two estimates. For period 42, you take the level of period 40, level. If you add 1.1, you take yourself to the next period. But that's period 41. So you take another 1.1, and this takes you to period 42. 378 plus 2 times 1.1. And similarly, if you want to make a forecast for period 43, so you start with a level of 40, and you add now 3 trends. And this is how you make future forecasts. Okay. So just a few observations before we move on. The trend at the beginning here is, I'm looking at what Holtz is giving me. As you see, it's around 6, 7. That's around what you have here. That's a trend. What happens at period number, say, 20? It starts to move down, and it stabilizes around 1 point something. So how did it happen? The time series started to decline. So the forecasts that used to go up created large errors. Holtz makes sure that those errors don't increase. It is taking care of that by reducing the slope. And that's what you see. It started with a slope that fits the first part, and it continues with the slope that fits the second part, which is an advantage over the regression. It's not always that Holtz is better. There are some time series that are very, very along a straight line. The regression will work. The Holtz will fit time series in which you do want to include the latest information because of possible changes in the time series. Very popular model, by the way. Now, why is it that we are saying that Holtz is forecasting a linear time series? Well, look how the forecasts are created. What happens here? The forecast for period 41 was by adding 1 trend. The forecast for period 22 was created by adding 2 trends. So the difference between this and this is 1 trend. And the forecast for the next period was created by adding 3 trends. So the difference between F43 and 42 is this trend. It's always the same difference. This is why when you look at the forecasts, here they are going along a straight line. This is why we say that Holtz is a prediction or forecasting method for a linear time series. What else here? The values alpha and gamma. So I took alpha and gamma 0.55 and 0.15. Okay. They might know the best values, and there is a way of finding what is the best value. I want to go to another example here, Holtz again. It's Holtz again. I can show this better on this example than on the previous one. So again, the story here is to try to see that you have linear trend, and we have a linear trend. I show to you how to calculate all those that I showed before. Everything is the same. But I want you to notice, I am using alpha of 0.1 and gamma of 0.5 in order to create the forecast for this time series. And this time series is represented by this line. Everyone will see that this is an increasing level, is increasing in a linear fashion. So you have linear trend, but positive, not negative. The slope is positive. Okay. So I'm running this Holtz method with alpha 0.1 and gamma 0.5. And I get a slope of negative 955. This is, you see, the slope of period 12. Period 12 will be the last period, negative 955. Something is wrong. It does make sense that Holtz will give us negative slope. So why did it happen? You'll see why it happened in here. That's the template that I'm using for Holtz. Like before, I plugged in 1.1 and 0.5 for alpha and gamma. Don't forget to put, then you don't even have, if you have my template, then it will count how many data points. If you forget and you type it, that's fine. You can type here 12 yourself. I created 6 forecasts into the future with 90% confidence because this was requested. But my point now is to show to you how the forecasting by Holtz compares to the time series. This forecasting procedure is terrible. It's always above the time series. At the very end is above, and because this one is so much below, the trend that it's giving you is negative. That's what happened here. Negative 955 is the trend that you see. So we have to improve this. I'm showing to you the prediction interval for exactly the same time series and the same forecasting. What you see here is what you see here. So this is the upper bound of the prediction interval, and this is the lower bound, 90% confidence. Well, look what happened here. The time series is outside the range all the time, almost. This tells you how bad this forecasting procedure is. How can we improve? We can improve it if we work on alpha and gamma that affect the forecasts, the errors, and then maybe MSE or MAE, any of those. And I want to find values that minimize, say, MAE. I do it with the data table here. I'm not going to ask you to do it in the test. I'm just showing it to you. So the data table, what I did, put all the alpha and the gamma values here that I want to check on. From 0 to 1 with increments of 0.05. And here I put all the values of alpha from 0 to 1, increment of 0.05. You can switch. Gamma can be here and alpha can be here. It just doesn't matter. What do you do then? You select the table starting at the corner here. What's in the corner? The function you want to work with. For example, I want to work with MAE. MAE is calculated in cell H5. So I made here this one equal to H5. And I select the table from this corner all the way down to the opposite corner. And then you go to data. And then you go to what if analysis. We did that in class, I remember, on 1-dimensional. This is 2 dimensions. And you go to data table. Then you enter on the row, you enter gamma. Gamma in row input. So you take the cell where gamma is given. You put it here. And alpha is coming in columns, so you put it here. If you click OK, yeah, because I didn't select. Anyway, if I selected the table and did what I did right now, it will, what is it going to do? Going to calculate MAE that I defined here in the corner to be my function for every combination of gamma and alpha. There are 400 different combinations here, 20 by 20. So it will do it 400 times. It will take very, very, very fast. And then you can select the cell where the best alpha and best gamma appear. It's colored because I use conditional formatting for that to make it easier to identify. But this is the minimum MAE in the whole table. So I should change alpha to 0.85 and gamma to 0.15. So look what is really happening when you do that. Alpha to 0.85, 0.15. And now is what I want you to see. First of all, the forecast is moving up. So the blue is the real-time series. Secondly, the interval is covering, and the real-time series is residing mostly inside the interval. Oh, maybe 1 point here, it's going out, it's hard to tell. Even if it is, you have 12 data points and in one of them it goes out, it's less than 10%. I did allow in 10% of the cases to not see a B inside the interval. So I'm within the allowed limits. And the interesting theory, what happens to the prediction interval? Do you see how much it is opening? So each one of them is 90% confidence prediction interval. As you move into the future, and the line is straight, you see, straight line. As you move into the future, the uncertainty increases and you have to provide a wider interval to make sure that you have 90% confidence that the real-time series, the continuation of the blue line will fall in it, inside. So that's what I wanted to show. That's why I went to the new example. But that's what you need to know about the holds. And yeah, you need to be able to enter your answers in the Microsoft Word file, type it the way you see it here. The way you see it here, not more. That's all what you have to show, and this will be the right answer. If you have such a question, you might have a question that doesn't even require all those. You might have a question that will have, that you will get this from the template and then calculate this one and this one, that's it. But you need to know how to run the template. Just as a matter of curiosity, take a look. Is it here? Oh, do you remember that for the regression, which was here, in 6 months, demand for beds will exceed the current demand because this number here was above 374. Well, when you look at the holds, you cannot argue this anymore because in 6 months, the lower bound is 357 and the upper bound is 412. One is below 374, one is above. Therefore, you cannot argue that number of beds in 6 months will exceed the current demand. Well, which leaves the hospital not that happy. But which result we should believe to, the regression or this one? I would look at the MSE, for example. This is not even the optimal, no, these are the optimal values, I think. And I look at the MSE here. I look at the MSE of the regression that was 225. and say that this model is so much more accurate than the other one, that I will take these results more seriously than the other ones. So this is the review on the Holtz method. I will stop here. I'll stop sharing, and I want to see if you have any question before we go to the inventory. Okay, so you talk with between the two of you, or more than two, I don't know. I think I said yes, it's going to be recorded. Oh, where did I do that from? I typed 1 instead of 41. Oh, period 41. Okay, let me see. Can I just see what did I do? So is it in the I guess you're talking for future forecasts. It will be here. Where? Oh, then you must be talking about the regression. Let's see. Ah, okay, I guess you understood what I meant. Thank you, though. Thank you. Okay, good. So now again, let me see if there are more questions. No, you are wrong. Linear, the seasonal model is going to be part of the test tomorrow. I even emailed to you a reminder yesterday about it. Yes, it is going to be there. That's why I'm going to talk about it again today. Okay. Okay, so you answering one another. Thank you, helping me out. Thank you. I fixed it. You are not going to have 9. I thought about 9 at the beginning, and then I said no, but then each question will have a lot, one mistake, and you are losing. So I'll have 15. I think I have 13 ready, and I have to write 2 more. And I decided to do it after I'm done with the presentations, so I know better. So it'll be 15. So now each question will be about 5%. And this is just fair, I think. Okay, I think you will be happy with the multiple choice because, look, not only I have hard time, you have hard time too, or the opposite. Not only you have hard time, it's a new territory for me too. So I'll help you, you'll help me out too. We have to work together here. And if you study seriously, really like I expect you to do, I don't see why you need 3 hours. I have to be very frank with you. And that's it. So no more questions. So I will, yeah. So I will go now to the next topic. And in the next topic, I'm going to do inventory that we didn't cover in class. So I do want to have a word about it. You'll be surprised how simple it is. And if You already looked at the text I sent to you with the pages I asked you to read. And if you tried some questions, you would see it's really elementary, but you have to read it. And inventory is very, very popular topic in logistics, in research, and in study, because it's easy. You just have to read it, and you will see from the concepts that you'll see today, this is all what you need to know. In general, guys, EOQ, or not EOQ, inventory systems are large and complex and expensive, and companies are trying to minimize costs. And this is the approach we are taking in our coverage. The EOQ model is the first of those models, very elementary, is dealing with a single item that needs to be managed over a very long period of time. The planning horizon is theoretically infinitely long, so demand will never finish, it will never stop. Think about margarine, okay? Not cell phones. Cell phones have a short lifetime, but bread, no. So we are talking an item that is ordered and being reordered and replenished all the time. And now the question is how best to handle such an inventory system. In an inventory system like this, we assume that the demand is constant and doesn't change. The demand rate over time is not changing. Not only that is not changing, we know what it is. Then the costs involved in running the system are also not changing at all. No inflation. So it's a very stable environment, okay? And the order, when received, it's coming in one single delivery, the whole order is shipped. All this, what I'm telling you, is affecting the way inventory is going to behave over time. So we'll go to the costs in a minute, but first notice, you ordered Q units, Q for quantity. Demand is constant. Inventory, therefore, drops along a straight line. No lead time is assumed to exist. Lead time is the time between when you place the order and when you receive the order. For the first case, there is no lead time. You order today, tomorrow you have your order available to you. So you will wait until the inventory drops to zero because there is no reason to order ahead of time. If you order ahead of time, you will have some inventory left when you receive the order that you will never use. This cannot be a cost minimizer. So you will be waiting until inventory is completely depleted, at which point you will receive a new order. Then you place a new order here. Question is, why would the new order be equal to the first one? That's because of the stability of this environment. If at this point in time here, you ordered Q and you were happy with this order because it minimized your costs, what did you see? You see a very, very, very long horizon with constant demand and costs that don't change over time. So you ordered Q. What do you see here? You see a very, very long planning horizon with the same demand and the same costs. So you'll order again Q. And this is how the profile of inventory in the EOQ method behaves. EOQ, by the way, economic order quantity. What we are looking for in this modeling is how much to order to minimize total cost. How much to order is the EOQ, also denoted by the letter Q with an asterisk. So I call it Q star. So which costs are we trying to minimize? Let's look over the definitions that will constitute the total cost. We need to know what is the annual demand. We call it D. We need to know how much we pay per unit when we bring a unit in before we sell it. We call it C. CH is the unit holding cost per year. There are costs involved in running an inventory. When the inventory is on shelf, you have costs. It can be insurance for the units. It can be a loan that you took from the bank, and the interest you pay is a cost, and you took it from the bank to pay for the inventory. It can be, preparations that you have to make to clean up the room because of the item is sensitive to dust. So all those costs, electricity, all those costs are per unit in inventory. And the longer the unit in inventory, the larger the cost. So what you pay per year per unit is CH. There is a simple way of calculating it. It's a percentage of the unit cost. Here it is. H is this percentage called holding rate. Multiplied by the unit cost, you get the CH. And CO is what it costs you to place an order. There are activities associated with placing an order that are independent of the order size. It's fixed per order. This is called C sub O. The larger C sub O, the smaller number of orders that you want, the larger the order size that you will order to cover more time until the next order. So with these definitions, you can come up now with the different annual costs. I want to, before go to there, to show to you the template, the inventory template. What do you enter here? And for this, I formed a small prototype example. So it's an item whose weekly demand is 150. Here you need the annual demand. So notice that I multiply 150 by 52. I entered here the unit cost of 15, it's here. I entered here 18% holding rate, it's here, so 0.18. Once you enter these two, the template will calculate CH by multiplying them. $2.70 is what it costs you to hold a unit like this for a year. And the ordering cost you enter here, 25. Once you added all those, you'll get results here, which we'll talk about in a minute. And those two. So we have here the annual ordering cost, annual holding cost, and annual purchasing cost. The easiest is a purchasing cost. You pay C dollars for each unit, and you buy per year D units. So that's how you pay to purchase D units and put it on shelf before you sell it. Now comes the ordering cost per year. For each unit, you pay CO dollars. In our case, take a look here. In our case, $25. Then you multiply it by the number of orders per year. Well, suppose you order 1,000 units. And suppose each unit, each time you order, it's for 1,000 units. For us, not 200 units. Then you do it 5 times a year, 1,000 divided by 200. That's why it's D divided by Q represents the number of orders per year. Multiplied by the ordering cost per order, and you find the annual ordering cost. In our case, 25 times 7,800 is the demand, and 380 is the order size. So how do we know that it's 380? We'll go in a second and you'll see that. Now, if you decide to order 300 here, then you divide by 300. It's your decision. Then the holding cost. Each unit in inventory will cost you CH dollars per year to hold. What do? Multiply it now by the average inventory. Why? Look at the graph here. The average inventory is here, Q over 2. So that's the average inventory all the year. Sometimes the average is lower than the real inventory, and sometimes the average inventory is larger than the real inventory. So overall, when you multiply by Q over 2, you get the correct annual holding cost. In our case here, you have CH, as I said, it's H times C, 2.7, times the order Q divided by 2. These two values are very close to one another. I'll go back to this point in a minute. So now we have 3 cost components here. If you add them, you get the total cost per year. Now these two are called total variable cost per year. And the reason is that the variable Q that you, the decision maker, has to determine appears only here and here. So only these two are affected by changing the order size. This one remains unchanged. And so to affect the total cost, you need to find the optimal Q, the one that minimizes the sum of these two, because this will not change anyway. Actually, this one is a sunk cost. So now comes the optimal order quantity, which will minimize the total cost of this plus this plus this. By the way, this is already the minimum. So as you see, the order quantity Q star is 380. How did we get this one? By this formula here. Okay, so what do you do here? I'll show it to you here. Okay. So it's the square root, and then you tell 2 times the demand. Take a look at the formula with the frame here. 2 times the demand times CO, which is 25, and then divide the whole thing by CH. But CH is 0.18 times 15 as before. So this gives you 380.58. It's rounded here. Yeah, it's rounded. So EOQ is Q star, is the optimal order quantity that if you order, you minimize your total cost. Because I entered here 380.06, and so I did here, so I am using here the Q star, and so this plus this plus this give me the minimum total cost, and this one plus this one, the minimum total variable cost. These two appear here. These are the minimum amounts. So I want you to know how to calculate the total cost. If I want you to show, say, how do you calculate the annual holding cost, and I give you 4 answers, one of them will be correct, you need to know how to come up with this and select the correct answer. So that's why you'll sit at home and do the small calculations and show it. But it's, you see, it's really, really, really simple. So that's the basic EOQ. There are a few more concepts on EOQ that I want you to see. It has to do with the reorder point. It has to do with the lead time. It has to do with safety stock. Before I go, I just tell you the template is allowing you also to change the order if just in case you cannot really use the optimal order because you are limited to say 350 units. It may happen when the supplier is the one who ship it to you with his own truck. And he says, you know what, I don't have space for 380 units. I can only ship to you 350. Now you want to know what will be the impact on your total cost. So you put 350 here, it will give you the total cost, and you can compare it then to the optimal, and you can decide if you want to go with this or not. So now I'm going to the second part of the EOQ here, okay? Let me take this one down, then I'll put it back. Here's what you see here. T stands for cycle time. L stands for lead time. Remember, before the lead time was 0 because you got your order as you ordered it. But this is not reality. In the real world, there are lead times. Sometimes they are very long. And so when you have a lead time, you have to change the timing of your order. You cannot anymore order at this time here when the order is received. You cannot wait until here, because if you do, you will have to wait L time units until you receive it. In the meantime, demand continues and you go into the negative territory. So you have shortages. That's not allowed. So you'll have to order ahead of time. How much L time units before the cycle is finished. And how do you know when to place the order? The easiest way is to find the reorder point. The reorder point is the inventory at hand when you place a new order. So how much is it? Well, it's easy to find. At the beginning of the lead time, you have inventory. We call it R, reorder point. At the end of the lead time, you have 0 inventory. And this means that during lead time, you sold exactly all your inventory here. So your inventory here is equal to the lead time demand. Lead time demand is equal to L times D. So the reorder point equals to L, the lead time, times the annual demand. If this is the annual demand, the lead time has to come in years. So let's assume that the lead time is 5% of a year. And the annual demand is 1,000 units. So the reorder point becomes 50 units. It's 0.05 times 1,000. So that's how you find your reorder point. Let's look at some more information that I'm giving you about the problem we started before, and we'll go back to the template to finish the work. First of all, I wanted to notice that sometimes you don't work with years, that is a very large time unit, but you work with working days, much more intuitive. But if you work with working days, it's not calendar days. So not necessarily the company is open for 365 days. In this particular example, I showed to you a company that is only working for 320 working days. So these are the only days where demand is generated. Therefore, you have to update your annual demand. So you have the old demand of 52 times 150, which is 7,800. Now you multiply it by 320 over 365, and what you are getting is this. Okay. The rest remains the same, 15, 18, 27. Okay, everything is the same. We don't need these two yet because we didn't talk about it yet. You see that EOQ now is affected because EOQ is dependent on the demand. EOQ is dependent on D, and D became smaller. So EOQ becomes smaller. Okay. So that's what happens if you work on a different, and from here on, we are going to use the 320 for the rest of the problem. Now I'm adding lead time that was not there before. The lead time is 3 days. The lead time is shorter than the cycle time, and this will be apparent in a few minutes when we calculate what the cycle time is. So the lead time is 3 days, but not good. It has to be in years. Well, a year is covered by 320 working days. So the lead time is 3 out of 320. The lead time. So I'll write here equal to 3 divided by 320. Okay. And this tells me that the lead time is 0.009 of a year. It's 0.9% of a year. So the lead time demand is the demand during 0.009 of a year. So you multiply them to find what it is. The reorder point is the lead time demand is the demand times 0.009, and this is the inventory at hand when you place your order. So what happens in this system, the inventory starts to drop until you hit a value of, now a value of 64 units, can you see our reorder point? 64 units, 0.10, and then you are placing a new order. You don't receive it right away, you wait for 3 days, and only here you are going to receive it. Incidentally, I want to tell you that when you see a reorder point of 64.10, and the item is coming in whole numbers, like you cannot have 64.10, but you have either 64 or 65, or 63, and so on. In this case, you will order at 65, a little bit higher, because to be on the safe side. Okay. So this is the issue of lead time. Now to this, we are adding safety stock. And I'm adding this for you to see what it means. Many companies are worried about shortages, especially at the end of a cycle when the inventory by definition is lower. And then a customer may come with a large order and shortages occur like you see in supermarkets today. So to secure or safeguard against too much shortages, they add additional inventory called safety stock that is on the corner, not been used most of the time, only been used when needed. And this has an effect on the reorder point, because if you order earlier than L units from the end of the cycle, order here. So now the lead time start its count at this point in time, and therefore it's going to be finished here before the end of the cycle. So at the time when the order is received, you still have some inventory. That's the safety stock. And therefore, at this point now you have replenishment and not at this point here. So the picture is changing a bit now. You start at a larger inventory than Q. Here you start at Q, but now you start at the larger inventory than Q because you have safety stock at the bottom. Here you have Q plus safety stock. You drop inventory all the way up to this point. This is the reorder point, but now it's the lead time demand plus the safety stock that you hold at the bottom. And so from here you have a lead time, and the lead time takes you all the way to the end of the cycle. You did not reach a value of 0, as you see. Now you have safety stock left. So now you place another order. The order size is not affected. It is still Q star as before. What is affected is the timing of placing the order that is now earlier to allow for the safety stock to be left at the end of the cycle. Of course, when you add safety stock, you have to add the holding cost of the safety stock to the previous costs. And the way to calculate it is CH, the unit holding cost per year, times the safety stock level. Okay. And so in our case, if you have 7 units of safety stock, as I mentioned to you here in part D, I'll add 7 here. And now look at the reorder point and look at the total cost. You see the total cost has increased, the reorder point has increased. And these are the only concepts that you need to know about the EOQ model. And well, wait, there is something about the cycle time and about the number of orders per year. So we already know the number of orders per year. In our problem here, it's going to be the demand, 6838, divided by the order size, 355. So this is the optimal number of orders per year because I'm using Q star when I divide here. 19.2 is the result. You may wonder, what does it mean, 19.2 cycles per year? Either you have 19 orders or you have 20, but you don't have 19.2. Well, that's because the year that we have taken is an arbitrary value. It was taken for convenience. The meaning of this is that in 1 year, there are 19 cycles fully completed, and the 20th cycle has started, but then the end of the year took place and the cycle was not finished. It will finish next year. So next year will not start with 0 inventory. It will start with some inventory, and that's what it means. And 19.2 now is just the average number of cycles per year. And now the cycle time. So the cycle time is the time between orders, consecutive orders. How long it takes for Q units to be consumed. It's a cycle time. So how do you calculate it? Very, very simple. Pay attention. It's very straightforward. You have n units, cycles in 1 year. Let's say I have 10 orders in 1 year. Well, these orders are evenly spaced because all order has the same size. So therefore, the time between every 2 orders is 1/10 of 1 year. And this is what I wrote here. T is 1, which stands for 1 year, divided by n, the number of orders. And so the result is coming in years. In our case, take a look. I also mentioned to you that it's the reciprocal of D over Q. 1 over N is Q over D. That's another way of calculating it. But in our example, you will have 1 divided by L39. L39 is, wait a minute. L39. So 1 divided by 19.2, which is the number of orders, of course, is 0.05. So about 5% of the year is a cycle time, which of course, it's not a workable value. You want to express it in working days. Well, we know that 1 year is 320 working days. So multiplied by 0.052, and you find that every 16.6 working days, you're going to place a new order. And this is it. That's the EOQ model. Ignore part E because it has to do with cycle time that is shorter than the lead time, whereas in our example, the cycle time is longer than the lead time. We are dealing only with this now. That's all. So that's the EOQ. Let me see if you have any question. Okay, somebody is doing my job. That's good. But tell me something. When I'm talking to you and somebody is asking a question and you answer him, don't you miss? Ah, you are going to read, to listen to the recording later. Okay. Okay, so there is no new question here. And so, and if there is no new question, which is fine, I will go now to the seasonal model, which is the third and last part for today's. Okay. Yeah. I don't know how many of you listened to the previous presentations on Friday and Saturday. So maybe it will be some kind of a repetition, which is not too bad. That's okay. But I cannot go into the many details because it's not the first time I'm doing it. I just do it to make sure that you grasp the concept. Seasonal time series has a very unique and clear pattern. Every given number of periods that doesn't change, the pattern within the cycle is the same. Can't say same, very, very similar. There is a typical behavior of the time series inside each cycle. Now, if we can look at the historical behavior and identify how seasons change the time series, we can use this effect in order to produce better forecasts. That's the concept. Okay. So now, a seasonal time series may include a trend, in this case, linear trend, or may not. So we allow for a trend, and later we can check to see if it was justified or not. Here is the equation that demonstrates the seasonal behavior. I will explain to you what is S1, 2, and 3 are. Y of t is the time series. It's equal to some linear trend B0 plus B1 times t. That's linear. Then we add to it a seasonal effect. If the seasonal effect, if the time is occurring in season 1, then the seasonal effect is B2 for season 1. If it's occurring in season 2, the seasonal correction will be B3 and B4 for season 3. And let's say we have a season 4, and I didn't include it here for a good reason. When you have 4 seasons, you will see only 3 seasonal variables. When you have 7 seasons, you will see only 6 seasonal variables, and so on. Always one less. Why? It will become very clear later. Okay. So now, the time series is being written in order to run regression for all the data sets here as equations as you see them here, but I'll go to that in a second. Now, let's assume that we want to write the relationship of this equation for period number 1. Period number 1 is here. So therefore, y1, which is 684.2, will be b0 plus b1 times 1. That's for the trend part. Now come the seasonal. S1, S2, and S3 are all dummy variables. Takes the value either 0 or 1. They take the value 0 if the time in question belongs to the season they represent. Because time number 1 is season number 1, and you will see it in the template in a minute, then B2, which goes with S1, B2 goes with S1, will be equal, B2 will be multiplied by 1. B2 times 1. B3 is multiplied by 0 because it's not season 2 and it's not season 3. Now, the next period, B0 plus B1 times 2 this time. Now we know that this is season 2 because the previous one was season 1. So B2 is multiplied by 0 because it's not season 1 anymore. But B3 multiplies by 1 because it is season 2. And B4 still 0. The next one will go similarly, it was 0 and 0, but 1 here. So you have the trend B0 plus B13 plus B4. And the interesting thing is the last one. Season 4 was not here. I didn't have a dummy variable for it. I don't need to, because season 4 is not 1, not 2, not 3. So that's why it's going to be 0, 0, and 0. And we are left with the trend variable, the trend component only to describe the time series in season 4. Okay, before I go now to ask what we do with the regression here, and let me finish the template here. So you enter the data here. And then you say, I have 20 data points. We have 20 data points. And then you say how many seasons you have. You don't have to worry about it. I'll tell you how many seasons there are. Or I'll give you a printout and you will know. So if I give you a printout with 3 columns here, then you know you have 4 seasons. Because once you enter the 4, like let's say nothing happens here. I didn't put anything yet. No number of seasons of columns were selected. But the template is programmed such that if you put the number 4, it will add 3 columns. If you add the number 7, there is such a time series that you have 7 days a week, and a week is a cycle. Ask a bank. They every day is different. Ask some retail, some fast food. They will tell you they have a cycle of 7 days. If I put 7, the template will put here 6 columns, you see. But I put 4 because we have a time series of 4. You can see 1, 2, 3, 4, and then 1, 2, 3, 4. So it's very, very constant. Well, this time series was selected, so it'll be easy to figure it out. So now you have columns of zeros and ones. The template is programmed, guys. Wait a minute. It's the template is programmed to start time number 1 with season number 1. So you have 1, 0, 0. That's how it is programmed. And this is why I started this way, not confuse you. So season number 2, the 1 will be here. Number 3 will be here. And season number 4, all of them are 0. What happens in Y5? Again, season number 1. So the cycle has 4 seasons. This is how it goes. Now what happens? You take this into multiple regression data analysis. So data analysis, regression, and Y is the time series here. X is all the range, time plus seasonal dummy variables. Everything is selected. All of them are the X range. And labels were selected. And T4, I want the data here. It will cover what we have right now. So this is the output. This output gives you the prediction equation here. These are the estimate of the beta coefficients. So I'm going to use them to make a prediction. Then the last section will be, how do we interpret the p-values here? I just do it because we did it so much in multiple regression, and this is multiple regression. So we can easily understand what this model is telling us. Okay. I want to make a prediction for period 21 because 20 is the last period, that's now. And I want to make a prediction for the next cycle, 21, 22, 23, 24, okay? This is what I want to do. Okay, so for period 21, 559.57 intercept, plus 9051 as the coefficient of time, times time 21, B0 times T. That's the linear trend element in this model. Now you add to it seasonal effect. This seasonal effect is negative. It tells you that you take the trend line and you reduce its value at time number 21 by 86. And then you get close to the time series. So the forecast will be the trend line plus the seasonal effect being negative here. So the coefficient negative 86 of the dummy variable of season number 1 is the seasonal adjustment. Time 22. Same thing, see? 559, 951 times 22 now, and the adjustment here is much larger negative. So season number 2 resides below the timeline, the linear trend line, 450 units below on the average. I skipped this one because it will be negative 130 and it's just the same as before. But take a look at season number 4. So now 559 plus 90 times 24 plus 0, plus 0, plus 0. Why? Because all the dummy variables in season number 4 are equal to 0. Now, how did I know that season at the time 21 is season number 1? Maybe it's season number 2. How did I know? Well, I did, because I look at the template and I see that this period 20 has dummy equal to 0, 0, 0, which means that period 20 is season 4. Then period 21 must be season 1. This is how you would know. If you don't have, unfortunately, a file and a template, but you only have an equation, suppose you only have this equation, suppose. Well, then you know that you have here 4 seasons. Then you go to the file, to the data, and you start with season 1. And you count 4 periods, and season 5 is a new cycle. And then season 9 is a new cycle. Just count, and you get to the last period. You see that it's season 4. Then you know how to continue. Okay. So I try to describe in a graph here how this time series behaves. So this is the trend line. Okay. Now I say time number 1, 2, 3, 4 as an example. It could be 21, 22, 23, 24. It's just an example. I know that time number 1 is season number 1, so I drop it from what? From the trend line. Drop it by 86. So you have 559 plus 9051 times 1, that's the trend line, minus 86, give you this value. Same thing I'll do with time number 2. I'll put the trend line here, minus 450, and this will be minus 130, and this one will coincide with the trend line. Because you don't need here a seasonal adjustment. But you have to be careful here for yourself. Don't think their season 4 is not part of the seasonal pattern. It is. The seasonality is for 4 seasons. But we need to draw the straight line somewhere. We decided that we are going to do it such that it will hit season 4. Each time in a new cycle, season 4, it will meet the trend line. That's our selection. Why did it happen? Because I eliminated S4 from the equation. So now the equation doesn't have it, and the time series is just hit the trend line. So what happened in the next cycle? The next cycle start exactly the same. 86, here it will be 86 below, and then 450 below, and 130, and you have another cycle and another cycle. They all look the same. This is the forecasting model. The only thing I want to add to you something here about the statistics, and then we'll all be happily ever after. First, we want to verify that it is justified to assume that you have a linear trend here. So you want to know if the variable time period needs to belong to the model. You test to see if the coefficient beta 1, which is the slope here, could be 0. So you put the null hypothesis, say beta 1 equals to 0. And you try to reject it. You reject it if the p-value is small, which is indeed so. So that's how you verify that it is justified to include linear trend in your model. Now you can say that the number 90.51 represents the average increase of the time series per period. This is why we do the test. Then comes the number negative 86. Don't be confused. I'm testing to see if it's true that a seasonal adjustment is needed in season number 1. So I test if beta 2 is equal to 0. If it is indeed equal to 0, then the time series, the trend line alone is enough. You don't have to adjust it with a seasonal factor. But if beta 2 is not 0, then you need the adjustment. Well, we test it and we see that the p-value is 0.37. There is insufficient evidence in this time series to reject the null hypothesis. So beta 2 could be 0, and the number -86 is unreliable. Yes, we wanted to adjust it like you see in the graph here, -86, but you don't need to. As opposed to -450. This has a p-value of 0.002. So now the beta 3 is not 0. You reject the hypothesis that it is 0. If it's not 0, you can work with a number -450. So indeed, in season 2, an adjustment of -450 below the trend line is needed. And then you go to season 3. Again, there is no sufficient evidence to say that beta 4 is 0, is not 0. It could be 0. So adjustment in season 3 is not necessarily needed, and the number 130 is unreliable. So are we saying that there is no seasonality here at all? No, because this is seasonal. Season 1 should be like this. You see, coinciding with the trend line. Season 3 should be like this. Season 4 then goes from 3 to 4. And this is the cycle. And then we'll start, and then this is season 4, this is season 1 again, right? But season 1 is on here. So you'll go from here to here, and from here down, and so on. In the real world, you will be doing it because you try to clean up the model from variables that are insignificant. But for us, in the test, in this course, we are going to stay with the model as is. I only want you to understand what these p-values say. I don't want you to make changes in the model. You can use it for predictions because of this significance F. That is excellent. So the model will provide good forecasts. For us in the course, at our level, it's good enough. So to make predictions, this is the procedure. Okay? I just wanted to indicate to you that there are questions that can be asked about it, and in the real world, you will be asking these questions. So that's all what I wanted to add to our discussion on seasonal multiple regression with dummy variables. There is a discussion about it. I sent you once an email from our text, chapter 8, at the end of the chapter, almost at the end of the chapter, they talk about this model. And I also sent you some problems that relate to it. And take a look at the examples that I sent to you. But this is about all what you need to understand. Not going to challenge you with more than this because of the conditions, because that's enough. That's really what you need to know here. Okay? Let me see what you want to ask. Okay, I don't see anyone is asking a question. Nope. Okay. So that's all what I wanted for today. I need now to convert it, and it's huge. It's what is it? It's almost, oh, it's, yeah, it's almost 2 hours, right? So it'll be a large file. It takes some time to convert. I'll then upload it to Dropbox in a folder that will have the name, the date. So it'll be 3/2020, and the time, I think, it's Zoom is doing it. And the time, it's a folder that includes the video with audio. And then a separate file, audio only, which I don't know if you even need, I'll leave it there. I'll add these files that I was working, these examples, to the same folder, so it'll be shared with you also. And so you will have it. I guess, I don't know if Excel can be downloaded to your own machines from a shared folder, but I'll put it there. Anyway, maybe somebody knows if you can download from a shared folder a file, an Excel file. Okay, so you'll have to try to understand it yourself, to try it yourself. I'm going to upload it. Okay, if you thought it was helpful today, just say yes. I want to see your response. Nice, nice, nice. Thank you, guys. You make my day, you know that. Okay, nice, nice. I'm happy. Fine. Okay, so now go home. Go home. You are at home. And do now your job. Just practice. It will take me some time. It's converting slowly. It's huge. And so it might take an hour until you'll see it on Dropbox. I'll start right away so that you can have it. And then wait on Wednesday, 10 delivery and 1 delivery of the exam. On Thursday, 10 delivery and 1 delivery of the exam. And please try to write it on the time that you are scheduled to take it in class. It will help me organize things and not get confused. Don't forget your name on the file. Okay? So thank you, guys.